Okay, so again, we have something flowing into a container and mixed solution flowing out. Concentration C1 comes in at rate R1. And the initial solvent has volume. Initially, you just have solvent with a volume of V0 with no concentration. Okay? So I might say no solvent. It's kind of implicit in the rest of the statement, but we might as well be sure we understand it. And then we have stuff flowing out at rate R2 times V. Why R2 times V? And actually it should be R2 times the square root of V. Because this is a uniform cylinder, and the way pressure pushes things out, according to Bernoulli's equation, which we really haven't done, but according to a very simple differential equation that we have seen, actually it's not according to that differential equation, it's according to conservation of energy. Okay? It has to be proportional to the square root of the depth. Okay? And since it's a cylindrical container with a uniform cross-section, implicitly, didn't state it, but that's how this rule can arise. The depth is proportional to the volume. Okay? So that's where this comes from, but right now you just accept it. I could make that V to the 47th power if I wanted to, and you'd still get an equation. Okay? Whatever this function is. So it doesn't matter that it's a square root or that I wrote it down as V first, because that was dumb. Okay? But we'll make it realistic. Change the shape of the container could be proportional to V. Anyhow, rate of change of Q with respect to T is what? And I asked for the simplest statement you could make without simply repeating the question. Okay? Without simply repeating what we already know. So the simplest statement you can make is so it's the rate at which solute flows in minus the rate at which solute flows out. Another thing it is, it's dq dt, which must be this, right? Because just by definition of what dq dt means, it's the rate of change of Q with respect to T. So we have an equation, dq dt equals rate at which solute flows in minus rate at which solute flows out. So dq dt in a little bit abbreviated form is rate in minus rate out. So what's the rate at which solute is flowing in? Well, for example, if it's 5% solution flowing in at 8 gallons per minute, then at what rate is solute flowing in?
Maybe 0.4.
You're trying to do a number, okay? And it happens to be right, okay? So that was good, but the easiest answer is 5% of 8 gallons, right? Instead of a number, how you get the number. And when you're solving a problem, you want to go through that step too. And you want to document it to make sure you know what your assumptions are in case everything blows up at the end and you got to go back and debug it, right? Which is the case 90% of the time when you're working on a challenging problem. Okay? So the rate in, well, if C1 is a concentration and the rate at which the solution's flowing in is R1, what's the rate at which solute is flowing in? Well, you said a minute ago should be 5% of 8 gallons per minute, right? You didn't say it, but that's what you did to get the 0.4. You didn't give me units either, it should be gallons per minute. But, okay. So what do you do with the concentration and the rate at which solution is flowing in to get the rate at which solute is flowing in?
Multiply them.
Yeah. And more specifically, you could say multiply C1 by R1, right? But that's implicit in what you said, but you want to be as explicit as possible. Just to make sure your thinking is as clear as possible, okay? And you could have easily said that, just knowing that it's probably a good idea to say it, okay? Okay, now what's the rate out?
Well, the rate's still the same. And
Rate stays the same? Nah.
well, no, you're right. It's whatever the second concentration is. Don't guess we gave it a name.
So it'd be minus C2 times R2 square root of V.
Yeah.
Okay?
C2?
That's great. What's C2?
Whatever concentration is in the container right then.
Well, so that would be this, right? So it just comes down to, for mixture problems, it's pretty much usually this. Rate in minus rate out. You just have to figure out rate in and figure out rate out. Now we're not going to solve this problem because there's a second differential equation has to be solved, which is the volume is a function of time. Since you're losing it at a rate that changes with volume, then you actually have to solve a second equation, okay? So you know what the volume is as a function of time. Turns out that's a fairly simple equation, fairly easy to solve, but it takes us a little beyond where we need to be when we're just starting with relatively simple equations, right? Now the problem that you're looking at is much simpler than this. What's rate in minus rate out? Incidentally, once we find V as a function of t, there's no guarantee that we're going to be able to solve this equation, although it does appear that it's separable. Can we do the integral? Now, once we get V as a function of t, actually it's not separable, but it's kind of first order non-homogeneous linear. There's a non-homogeneous part. This is linear in Q, right?
So do the integrating factor?
But might not do you much good because V might be a complicated function. You're going to end up with the square root of V in the denominator. Okay? And it might be nasty to integrate. Not guaranteeing anything. Okay? So we probably solve that equation too. But right now, we're not going to worry about it. I just wanted to illustrate the fact that no matter what you do, the first thing you want to do is dq dt is rate in minus rate out, where rate is the rate at which solute is changing. Okay? So the rate at which solute flows in minus the rate at which solute flows out. Okay? So see if you can do that equation, because I think you have a situation where you have a constant rate of flow out. Okay? And that makes it much easier.